Thank you. Um, Good morning from here. Good evening to you if you're in the evening time zone, and I don't know whether to say good afternoon and then maybe good night. Um, my name is Gideon Uchehara, and I'll be presenting on simulating large quantum circuits on a small quantum computer. Am I coming out loud enough? Is this loud
Yeah,
enough?
we can hear you. Yes.
Okay, yeah. Thank you. So the outline for the presentation is just like this. I'll be talking about circuit cutting, and anytime you hear cut QC, it simply means circuit cutting. I'll use those terms interchangeably. I'll go over the overview for circuit cutting, then I'll go over the background to circuit cutting. I'll go over the lemma behind the idea of circuit cutting, then I'll go over examples of circuit cutting with 1 qubit, and I'll look at multiple qubit or multi-qubits, and I will go over how to implement this using penny lane. So what is the motivation for this? Let's say you have a quantum circuit or a problem that you want to solve, and that problem requires a large quantum circuit compared to the quantum device that you have, let's say a quantum computer that you have, and you would like to run this problem with large quantum circuit, large in the sense that it has more number of qubits than your system can provide for you. You want to still explore ways that you can solve this problem with your small quantum computer um, without having to wait ages until the right quantum computer that solves your problem arrives. And so that is what I try to present in this tutorial. I want to present how we can use small quantum computers to solve problems that require large number of qubits. So given the problem, which is the quantum circuit that you want to solve, um, you can, if you have the required device with the number of qubits that your quantum circuit requires, you can simply run that through your large quantum computer and do the measurement and get the measurement outcome. And that's pretty much straightforward. And like I said, today's in today's in today quantum computer, we don't have such large quantum computer. Assuming we don't have that kind of quantum computer to solve your problem, then this method is a method that you can consider, which is the cut QC method or the circuit cutting method. And what this does is that you first of all you have your circuit, you determine a location that you will cut such that you maximize the number of qubits that will fit into your device and split that circuit into subcircuits and run them on your small quantum device. Let's say you split the circuit and it resulted into two subcircuits, one subcircuit, the first subcircuit, and then the second subcircuit. You can take them individually, run them through a quantum circuit, your quantum device, and get an output, get the measurement for the second quantum subcircuit, run it through your device, and you get measurement out of that device. So what then do you do from the result of the measurement? What you do with the result of the measurement is to combine this result using some classical post-processing. So we use quantum computer to measure the subcircuit, but you require some classical post-processing, which does not involve quantum circuit or quantum computers, to be able to combine this result from the subcircuit 1 and subcircuit 2. And hopefully, our goal is to make sure that the result we get afterwards, it's approximately equal to the result that we would get if we had a large quantum computer that is capable of running this quantum circuit without having to cut it. So that is what we set out to do in this tutorial. One example is this. This example is taken from this paper by Tang. It's a quantum circuit that has 3 qubits. And in this 3-qubit quantum circuit, we have a quantum device that can't run. Sorry, this is a 5-qubit quantum circuit, rather. And with this 5-qubit quantum circuit, we have a quantum computer, let's say, that can only execute 3 qubits at a time. How can we run this quantum circuit with 5 qubits on a quantum computer that can only handle 3 qubits? And this is the way you do it. With this quantum circuit, you choose a location. In this case, the location is on qubit 2 at this point, and cut the circuit such that after cutting, you have 2 subcircuits. These are the 2 subcircuits, the upper part and then the down part. So usually I refer to the upper part as subcircuit U, upstream subcircuit, and then the subcircuit 2, which is downstream subcircuit, I refer it as subcircuit V. And the next thing is how to combine these using classical reconstruction or classical post-processing. That's what we'll want to set out to do. Now, before we get into the nitty-gritty of how to get this done, it is good that we revise some background to understanding this. And it is important, I know it could be that some of you are pretty much familiar with these concepts, but I just want to refresh that so that we can set the background for how we came about circuit cutting. A qubit is the fundamental or the basic unit of information that we have in a quantum computer, and it is to a quantum computer what a classical bit is to a classical computer. The general representation for a qubit is given by this equation. That's equation number 1, where you have psi is equal to cos theta over 2, and then the state 1, and this is the phase, e to the I phi, sine theta over 2, and then the 1 state. So this is basically a superposition of states. So from this equation, we can get the state of any qubit, or we can represent the state of any qubit, be it a qubit that lies only in the on the z-axis, in which case, let's say the 0 axis, in which case we don't have this, and it could be that this qubit is a quantum state that lies just on the 1 state, which is this. So we can come up with whatever state that we want using this representation for a qubit. Now, that being said, we want to see how to get information about this qubit. How can we get information about the qubit? So that is what observables are all about. Observables are the measurable properties of a qubit or a quantum system. In this case, I have specified qubit because that's what we are concentrating on. And we can measure properties such as position, spin, energy, momentum, etc. And these observables, we know, is that they are always Hermitian matrices with eigenvalues that represent the set of measurement outcomes that you can get when you measure these properties of a qubit. And also, measurement gives us useful information about the state of the qubit. I've said that. So if you want to find out what is the position of this qubit, you do measurement to get that. So, and I just noted here that a Hermitian matrix is equal to any matrix that is equal to its complex conjugate transpose. So that's just to explain what Hermitian matrices are. Now, the next thing is that there are commonly used observables, which are the poly X, poly Y, and poly Z observables. And the eigenvalues for any of the poly observable is either +1 or -1. And then the X is represented by this matrix, the Y represented by this matrix, and the Z represented by this matrix. For the purpose of this tutorial, it is important to introduce these poly eigenvalues again. Sorry, poly observables rather. Now, what happens when we measure the poly observables is that the state of the qubits that we measure corresponds to the eigen. Sorry, if we measured a qubit in a particular state, then the value that we get is the eigenvalue of that observable, the Hermitian matrix. And if, for example, we measure the poly Z observable and we notice that it is in state 1, then the eigenvalue we get is 1. Or if, let's say we measured the poly Z observable and we get an eigenvalue of 1, then the state of the qubit will collapse to the state 0. If we measured it and then we get outcome -1, then the state of the qubit would collapse to state 1, which is the ket 1 here. The same thing applies to poly X and poly Y, in which case you have the eigenvectors to be plus state, the minus state, the plus I state for poly Y, and then the minus I state for poly Y. And this is representation for the plus, minus, and plus I and minus I state. This equation 3 here represents that. Now, it's also important that we talk about expectation value because it's important for what we'll be talking about later. So, because measurements are probabilistic, it is important to ensure consistency in the measurement outcome. And so the weighted average of the measurement over many of the observable is known as the expectation value. So we take several measurements. We measure the circuit because quantum circuit, when you measure it, it's probabilistic. You take as many measurements as you can take the average of this measurement. That is what expectation value is all about. Now, if we are given some state psi, this psi, I've taken it from equation 1 that I introduced earlier, which is the general method to represent a qubit state. So we can compute the expectation value for the different poly observables as follows. So we know that this is the way to represent expectation value, where you have the bra and the ket notation over the observable that you want to compute. So if we had the quantum state that we saw earlier for a qubit, this is the X, this is the expectation value for observable X, and this is the expectation value for Y, and this is the value for Z. Now, if you look at this equation very critically, and you will see a relationship between this equation and the spherical coordinate. The spherical coordinate you have is the coordinate that represents, it helps us to visualize a sphere, and it has a radius, an inclination angle theta, and then the azimuth angle phi. There is a relationship between these coordinates and the result we get from just computing this expectation value. And that relationship is such that the sphere that comes out of this expectation value will be seen as a Bloch sphere with radius 1. So that is what a Bloch sphere is all about. Bloch spheres in general are used to represent the state of a qubit on the surface of the sphere. So we know that any state, any position in the sphere can be represented using these three values. The same way we can use these three expectation values to represent the state of any qubit, single qubit. For emphasis, we can represent the state of any single qubit on a Bloch sphere using this method. So if we know the expectation value of the qubit along the x-axis, we know its expectation value along the y-axis and the z-axis, we can perfectly represent or tell where the location of this of the qubit is on the Bloch sphere. That's the point I wanted to make here. So if we look at the state psi and we say it's located at some point P on the Bloch sphere, then we can define P to have these different coordinate points. the x coordinate point is the sine theta, sine phi. The y is the sine theta cos phi, and the z on the z-axis is the cos phi. So this is basically like looking at a three-dimensional object, and then you have the value of that, the value of the point along the x-axis, along the y-axis, and along the z-axis to be represented by this. So, and I've made this, I've tried to simplify this by specifying them as the point along the x-axis, that's p sub x, p sub y is a point along the y-axis, and p sub z is a point along the z-axis. So the number p sub x, p sub y, so like I say, they are actually the expectation value along the poly x-axis, poly y, and poly z-axis of the block sphere. So as you can see on this block sphere, you have the poly x, poly y, and then poly z-axis. Another thing that I would like to introduce is the density matrix. The density matrix is very important because this will form the background for what we'll be building up on. The density matrix is just a way we can represent, it's an alternative way to represent the state of a qubit or a quantum system. So in this case, let's say that we're given a 2 by 2. Let's say we're given a pure state, which is psi. And let's remember the psi in equation 1. The density matrix is the product of the outer product between the bra and the ket of psi. So that is the psi times its conjugate transpose. So that is what this is all about. So the density matrix on its own is a self-adjoint matrix that describes the state of a physical system. So for a two-level system, which is something like a qubit, it is a 2 by 2 matrix. So it can also be used to represent pure states and as well as mixed states. Also, we can simplify the density matrix using the poly observables or the poly matrices that we saw earlier, which is the poly x, poly y, and poly z. So this is what you're going to see in equation 7. So here we have some density matrix rho, and this density matrix can be expressed in this form: the identity times some vector. If you remember this vector p, which is a point on a block sphere, times dotted with theta, which is, and theta here is like a vector of the poly observables x, y, and z. So this is a general representation for any density matrix. Given this representation, if we make this substitution, if I substitute for p and for sigma, then we're going to have this. So density matrix, representing it in matrix form, is going to be in this form. So what do you see here? You will see that the expectation value along the z-axis is pz. They are all on the diagonal part. One of them is positive, the other is negative, while the off-diagonal terms are comprised of the expectation value along the poly x-axis and then along the poly y-axis. Now, this is important because this is the basis for circuit cutting. If we take a second look at the density matrix, you will see that if you recall here, this is the density matrix here. If you make this substitution where you have, the expectation value, this is the trace of rho and I, trace of rho and x, and trace of y and y, trace of z and z times z. So what this means is that this trace operation here, actually the expectation values that we saw earlier. So in quantum computing, you know that when you take the trace of something, that the trace of the quantum system with respect to an observable, then you are actually taking the expectation value of that observable. So in this case, we are looking at the expectation value of the operator the operator I, given the state rho. And here we're taking the expectation value of x, given the operator, given the qubit rho. In this case, we are taking the expectation value of y, given the quantum state rho, as well as for z, we do the same thing here. And this is not different from the point p that we earlier computed for, except that in this case, the trace of rho and the identity, which is the expectation value of the identity matrix, is just 1. So 1 times this will return us back to this identity there. So the trace is corresponding to the expectation value along the expectation value of poly x, which is the p sub x, and the expectation value of poly y, which is p sub y, and so on. So that said, you can see the connection between the expectation value on the Bloch sphere and the density matrix. The trace operation, we have shown that it is related to the expectation value of the expectation value of the different observable, poly observable, for this given density matrix. So that being said, this sets the stage for us to manipulate this density matrix before we can establish the point for the circuit cutting. I don't know if there's any question to this point before we go on. Is there a question? All right. So now we want to look at a different way to express the different poly observables, and this is just a way to express the identity poly x, poly y, and poly z, and we're expressing them with respect to their eigen projectors and then eigenvalues. So for the identity, this is the eigenvalue for the identity is +1 and then +1 again. And the states, it can either be in state 0 or state 1. So that is the eigenvectors for this identity. Now, for the poly x, it has eigenvectors of plus and minus. For plus, it has eigenvalue of +1. For minus state, it has eigenvalue of -1. Same for poly y, the eigenstate is plus I, and then and minus I, and their respective eigenvalues are +1 and -1. Same applies to z. That is why we can represent them this way. So this on its own, this is called the eigenprojector for this identity, and this is also another eigenprojector, which corresponds to the eigenvector of this, the other eigenvector for the identity. Same applies to all the other poly observables. Now, why did I have to introduce this? Is that if we substitute these expressions back into this equation that we have here, then we are going to have this equation here. So basically, you have some trace operation, which is some expectation value of some observable, and an initialization to some state, which is the eigenstate, measurement, the expectation value of I, and then the initialization to another eigenstate of I. The same thing we do for x. Take the expectation of x and then initialize the circuit to its eigenvector. Take the expectation of x and initialize the circuit to its second eigenvector. We do that for all of them. So in total here, you're going to see like the there are 4 observables here times 2 because they all have 2 eigenvectors. Now, if we do that, we have summation over 8 different terms. In this case, we have some trace operation, which is the expectation value, and then some initialization, which is these eigen projectors here. And then the CIs here are the eigen value for the different eigen projectors. So this half, you remember it from the density matrix. So if we further simplify this equation, equation 12, that's this equation. We are going, sorry, if we further simplify equation 12, which is this equation here, we're going to like basically take each of the observable, group each of the observables with, sorry, we are going to group the different eigen projectors and the observables differently. So if we simplify it, we have trace of rho and the identity, and trace of z, which is the expectation value over I and the expectation value over z, and then the state 0. So basically, if you do this substitution, just play with the arithmetic, you're going to arrive at this equation here. So that is why basically I just group different terms together and split it into 4 different terms here: rho 1, rho sub 1, rho sub 2, rho sub 3, and rho sub 4. And these are the different values for rho sub 1 all through to rho sub 4. So in this, yeah, just for emphasis, I have made the following substitution that for x and for y, if you see here, we don't have plus state anymore. Sorry, we don't have minus state and then the minus I state anymore in this case. The reason is because of this substitution that we made here. So we made this substitution here into this equation, and that's what resulted into this. So just to emphasize that. Now, I have introduced us to density matrix. We've played with some mathematics on how to rewrite this density matrix to fit into what we want to discuss, which is circuit cutting. Now, the first paper that talked about circuit cutting was this paper, How Simulating Large Quantum Circuit on a Small Quantum Computer by Peng et al. And what the paper says is that if we look at a quantum circuit as a tensor network, and this tensor network has an edge, it has vertices, and the edge and the vertices can be represented by this graph, or the tensor network can be represented by some tensor network, which is the A value, by some tensor, which is the A here. It says that there are some 8 coefficients. If you recall back from this equation here, how we came about this 8 summation term was from this 8 term. Counting this, you're going to have 8 terms here. So there are these coefficients here, Ci, which consist of minus half and plus half. So if you recall back from the density matrix, the half that was there in the density matrix has been brought in here. And so since the eigenvalues are either -1 or +1, the half has been, the half has kind of, that came into the summation term, making it Ci to the half here. And so what you're going to see also is this observable and this initialization. So if we take a qubit flow, let's say we started a qubit from U and then to V here, it says that if we cut some points of this circuit, of this qubit, let's say we cut the middle, it is not different than just having the qubit initialized at the point of cut with some observable O sub I, and at the other cut end, sorry, it's the same thing as measuring the qubit at the first end of the cut with the observable O sub I, and initializing the other end with rho sub I. If we do this over all the poly observables, or over all the possible observables, which in this case are 8 because they are repeating, 4 repeating observables here, and this we initialize the other part of the circuit with the different eigen projectors or eigenstates, then if we take the measurement of this and combine it with the measurement of this using tensor network, the expectation value we will get for this is still the same thing as the expectation value we would have gotten for this circuit. There's no time to go over the proof, but this is just a simple explanation to this concept or to this lemma. So in general, if we picture, I've explained this, the flow of qubit from U to V as a line between point U and point V, then if we cut this line at some point, we can recover the qubit state at V using this equation. So recall this was the original density matrix, and at some point we cut this density matrix, or we cut the qubit, and we use this equation to recover whatever the qubit would have produced at point V with this equation. So the expectation value we will get with this equation here is the same as that we will get without cutting the circuit here. Is there any question? All right, so to explain equation 13, we see the trace operation, and this row here, we consider it as a quantum map that can be implemented by first we measure some observable for that circuit or the qubits that we got, and then we prepare the corresponding eigen state, which is rho I. So if you recall here, we measure this part of the cut with this observable, and then we prepare the other part of the cut with rho sub I. Now this is a vivid example of what we're going to be looking at today. First, we have this circuit, and remember the flow of qubits from U to V. Here, just look at this qubit here in between this point. This is where I chose to cut. Anybody can cut at different points, but just for simplicity, I chose this one qubit to introduce the idea. Now at this point, I did the cut. So this cut here produces this subcircuit. The first subcircuit is this part. The second subcircuit is this part. For the first subcircuit, we have to measure in the different observables. So that's why I have, this is the column for subcircuit U, this is the column for subcircuit V. For subcircuit U column, you have this measurements to do. Measuring of the polyeigen value, O sub I, measurement of all through to O sub A. So recall that I should have included the value, what O sub I and O all through to O sub 8 is. But if you can recall from here, coming back to this point here, the O sub I actually I, so O sub 1 is the identity, O sub 2 is the identity, O sub 3 is the poly X, O sub 4 is the poly X as well, O sub 5 is the poly Y, O sub 6 is the poly Y, O sub 7 is the poly Z, and O sub 8 is the poly Z. So you see that each of the polys takes two observations. It's measured twice for the circuit. So why is that? Is because each poly has different eigen projector, which is a 0 projector for the identity, the 1 projector for the identity, and so on. Plus for X, minus for X, plus I for Y, minus I for Y, and 0 for Z, 1 for Z. So that's why you have the 8 terms there. That's why you have these 8 summation terms here. Now for the V part, we initialize with rho I. Rho I are the eigen projectors. That's why you have row 1 all through to row 8. And if you recall from what I did before, in this case, row 1 is going to be the 0 state for the identity. Row 2 is going to be the 1 state for the identity. Row 3 is going to be the plus state for the poly X, and so on and so forth. So with this small circuit has been broken down into 8 different subcircuits. Sorry, 8 different summation terms. Each of these summation terms having 2 subcircuits. Is there any question? All right, no questions. I am assuming that we all understand what I've explained up to this point. Now, that said, what we will do next is to measure the different observables here. Before we do that, what I did here was to just show you what happens when you don't cut this circuit. Without cutting the circuit, this is the result we expect. I didn't apply any cut on this circuit, so this is just penny lane framework. There's no cutting applied to this, and this is the expected result. Let's see if we apply the cut, what the result is going to be. Recall back that this was the circuit that we had, and we applied a cut here. These are the sub-circuit that were generated from the cut. Now, for the subcircuit U, there are different terms here. There are different measurements to do. The first measurement is to measure the identity, get the expectation value for the identity, get the expectation value for the poly X, expectation value for Y, and also for Z. These are the values that I got from doing this measurement. And I'm sure it's a simple circuit that we can verify by inspection. So that said, we do the same thing for subcircuit U. In this case, we have, we measure in the 0 basis, 1 basis, plus, and I basis. Why did I choose 4? Sorry, okay, this is 4 because even if I measure X, I can't, repeating X is like doing the measurement twice. It doesn't make sense. It will always give you the same result. But why did I choose here to measure only 0, 1, plus, and minus, plus and plus I? Is because if you recall the substitution that we made here, is because of this substitution that we made here. Here you can see that we don't need the minus I state and the minus state. So because of this substitution, there's no need to use the minus state. You can find it in this equation here. So that's why we didn't have to measure that. So back to this point. So we've gotten all the measurement terms that we need. For subcircuit U and for subcircuit V, we've gotten all the terms. Now, the next thing is, how can we combine this result using the summation term that we had? So we simplify the summation over 8 terms to summation over 4 terms here, which is represented by this density, by these equations here. Now, the goal is to combine the results that we got. Remember the trace of row I, row Z, we already got them from here. This is the same as the expectation value. So for I is 1, for Z is minus 1, and for X is 0, Y is 0. So we have to make the substitution here. We got this to be 1, we got this to be minus 1, we got this to be 0, and this to be 0. So basically we don't need this. We just, the answer, the expectation value or the probability will depend on this result here. So that said, this is how we combine the result. Is there any question? Now, the next thing is to how do we combine this result? And this is the way we combine the result. It's just simply applying this equation to it. And In this case, we already computed expectation value for x, for I, for x, for y, and for z. And we got the probability outcome for the different initializations. So recall that this initialization gave us this probability outcome. This initialization gave us this probability outcome, and so on and so forth. So take note of the difference. In subcircuit U, we measured expectation value. Subcircuit V, sorry, this is supposed to be V, not U. We measured probability distribution, and we combine the result from the expectation value and the probability distribution we have for these different initializations that we have here. So this is a simple function that I created to do that, and as you can see, the result from cut QC is exactly the same as the result we get from the uncut circuit. Is there any question before I move on? So that's the end for this for 1 qubit cut. Leah, how many minutes do I have left?
We left it flexible, so you can make your judgment on that. If you think there's something you really want to cover, you should go for it.
Okay. All right. Well, I still have some more slides, but let me go over the second one, and maybe we can stop because I wouldn't want to bore you with too much details. Now, we did 1 cut for a single qubit circuit. How about when you have multiple qubits quantum circuit? What's it gonna be like? Actually, there's a little twist to applying cut QC to that, and that's what I'm going to share with you. But this approach is going, if you apply this approach, it works for 1 qubit and it also works for multi-qubit circuits. So, and this is where you see the power of cut QC. If you recall, if you read the tutorial that I shared before, we had a problem with Jimmy, who wanted to solve some problem with his photonic quantum computer that requires 5 qubits, but he had a device with 3 qubits. So we want to visit that problem again. Now, this is the problem that Jimmy wants to solve with the 3 qubit quantum computer, but this is 5 qubits. So how can we solve this problem? First, let's inspect what the outcome of this would be if we had an ideal quantum computer with D that can run 5 qubits. In this case, it's very simple because we can do that using a simulator. If we simulate this, this is a quantum circuit that I defined, and if we run this using the Q node and the device, we are going to get this probability distribution here. So this is the probability distribution that we're going to get for the uncut circuits. This is without applying cut QC. Now we want to apply cut QC to this original circuit, and in this case, I've chosen to cut this circuit on qubit 2 at this point of the qubit. Now I've chosen a location and I've made my cut. After the cut, I have 2 subcircuits, subcircuit U and subcircuit V. Now we have to identify the terms to compute for the 2 subcircuits, and the terms we need to compute are, as you can see in this figure. So it is the cut location. For the cut location for subcircuit V, we have to initialize with the different observables. In this case, I, X, Y, and Z. We have to get expectation values for all of these observables. And for subcircuit V, we have to initialize with this different state, 0 state, 1 state, plus and plus I state. Now that said, there's a rule that we have to take note of when we compute this expectation, when we compute expectation value for subcircuit U. And this is the rule. As you can see from the figure that I showed before, the terms we need are not different from those that we needed from subcircuit 1. For subcircuit 1, for the 1 qubit cut that we did before, 1 qubit quantum circuit that we did before, we had just one qubit cut. It is not different than what we have to do here, and we measure the poly I, poly X, poly Y, and poly Z observables. It's the same thing that we have to do here. However, one thing is worth noting is that we are working with multi-qubit. There are, apart from the cut qubit, there are also uncut qubit that we need to account for. So the expectation value for subcircuit U and the probabilities for subcircuit V will depend on the state for which we would like to determine its probability. So here in this case, we have 5 qubits, and there are, if you want to find the probabilities for these 5 qubits, we know that there is like 2 to the power of 5, which is equal to 32 different states that we need to compute their probabilities for. So it starts from the 0 state all through to the 1 state. So, and this is the way you represent a 0 state all through to the 1 state. In total, we have 32 states to find their probability. So, and let's say we are interested in computing the probability for this state, the 00100 state, this state here. And recall that we had made a cut on qubit 2. So here we have 0, qubit 0, qubit 1, qubit 2. So we made a cut on this qubit where the state is 1. Notice if we cut this circuit, remember that part of the circuit goes to subcircuit U and part of that qubit goes to subcircuit V. And that's why for subcircuit U, we have the state 0, 0, 1, starting from here all through the point of cut. And for subcircuit V, we have from 1 all through to the end, which is 1, 0, 0. So you see that both of them share the qubit that was cut, which is the qubit 2, and it's in state 1. Now, the next thing is to compute the expectation value for subcircuit U over the states 0, 0, 0, and 0, 0, 1. So here, because we are interested in the cut qubit, the cut qubit can either take a 0 state or a 1 state. Because it can either take a 0 state or a 1 state, we have to compute the expectation value over this states 0, 0, and 0, 0, 1. Also, notice that qubit 2 has taken on 2 states. So that's the state here is the 0 state and also the 1 state that it has taken here. So we have to take note of that. And the implication is that we would run circuit to measure the uncut circuit in the computational basis and measure the cut circuit in the poly X basis that we are initializing to. So the point is that because we had some uncut qubit in subcircuit U, those qubits will be measured according to the original expectation value. According to, in this case, we are not looking at expectation value, according to the computational basis. So let's say if we go back to this point, this is the subcircuit here, and we cut subcircuit Q2. So recall that these qubits, qubit 0, qubit 1, were not cut. So we measure these 2 qubits in the normal computational basis. But for this qubit here, we have to measure it in the I basis. And the same thing here, measure these 2 qubits in the normal computational Z basis and measure the cut qubit in the X basis. The same applies here and so on and so forth. So that's what that rule is trying to emphasize. So from the resulting probability distribution that we get from measuring that circuit, given the basis that we have chosen to measure for the cut qubit, you're going to have some probability distribution, but because in this case you're interested in probability. So if I measure that circuit and guess probability distribution or the probability outcome for the different states that will come out, in this case, since there are 3 qubits, we expect to have 8 states. So out of the 8 states, we are interested in the states that correspond to the state that we want to compute its probability for. And recall the state I wanted to compute its probability was 00100. In this case, because we are considering the cut qubit, it can take on 000 or 001 states. And so we have to compute the probability for this state, the expectation value given these states 000 and 001. So it is the probability for this state that we would use to compute the expectation value for the poly observable that we are measuring the cut qubit with. So except for the poly y, and this is another rule that we should take note of, except for the poly y, for the poly I, whose eigen values are both +1 for all other poly observables, we need to compute the expectation value as follows. This is the way you compute the expectation value for all the other observables. So if, let's say, I initialized or I measured the cut qubit with poly X observable, and I know that poly X observable has two eigenvalues, which is the +1 and then the -1. I know that it is +1 if the state of the cut qubit is in 0 state, and it is -1 if the state is in 0 state. So here, the cut qubit is this last qubit. If the state is in 1 state, the eigenvalue is minus. If the state is in plus, so if the state was in 0 state, then the eigenvalue was, the state is in 0 state, the eigenvalue is plus, and if it's in the 1 state, the eigenvalue is 1. So what this means is that if you get the 8 probabilities that you would have gotten, the 8 probability distribution for the different states you would get from measuring the circuit, if I take only the probability for 001 and 000, then I would multiply the 001, the probability value for the 001 outcome, by +1, and that for the for the one for 000 outcome, I'll multiply it by +1, and that for 001 outcome, I'll multiply by -1. And take the sum of these, we know that that's what expectation value is all about. So it is the probability of that state times the eigenvalue for that state. That is what expectation value is all about. So that's exactly what happens here. So in this case, it's a little bit rigorous to compute the expectation value because we have to take into account the specific states that we're interested in computing its probability distribution. So if you go into the note, you will have details. There are details of how to do this in the note with the code that I have provided. So let's say we want to compute the expectation value for this subcircuit here, and we're expecting to compute in this subcircuit here, to compute the expectation value for the identity here. If I can use my pen. Now, this is subcircuit U001. So here, I'm expecting 0, 0, 1. That is the state that I'm interested in. But because this state was caught, it can either take 0 state, oh, excuse me. So because this state was caught, it can either take the 0 state or the 1 state. So in this case, if we measured this, given this, this was in the Z basis, measured in the Z basis, this was measured in the Z basis, and this was measured in the I basis, as we can see here. If we measured it, we're going to have some probability distribution for 0, 0, 0, 0, 0, 0, oh my. So we'll have probabilities for 0, 0, 0, 1. Why is this messing up? So we have 0, 1 0, and so on and so forth until we get to like 1 1 1. So the point I'm trying to make is this: we are interested in the probability distribution for the probability outcome for this whole measurement. But at this time, we are considering subcircuit U, and which is from this qubit to this qubit here. So in order to compute the probability distribution for I, probability distribution, given that we are measuring the cut qubit in this state, sorry, in this basis, which is the I basis. Let's say after measurement, the probability outcome here, let's say 0.5. Let's say this was 0.5 and this was 0.5 and so on and so forth. Then, let's say if this was 0.5, 0.5, and so on and so forth. So, if this is 0.5, 0.5, all the rest will be 0 because the summation of the probabilities here will have to be equal to 1. And since we are computing the expectation value for, this is supposed to be expectation value for Z, Z, I. This is the most interesting part. That's why I'm taking my time to explain it. So since we want to get the expectation value for this, this is going to be equal to this. So this is 0, 0, and this can either take 0 or 1. So in this case, if it here is 0, then we are looking at this state here, and we know there's the probability value to be 0.5. And because it is 0, then we multiply it by plus 1. That's the eigenvalue for the 0 state. Then the next state was supposed to look at from this probability distribution is supposed to be 0, 0, 1, and that's this. The value is 0.5. 0.5. We multiply this by, so multiply 0.5 by minus 1. Why is this? So when we multiply this by minus 1, if we add them together, the result is going to be 0. So this is just an example to show what I was trying to explain. Oh my. So I think I lost the whole thing. So,
I think you're good.
Yeah. So that's the point I was trying to make. And this is it here. So if we add this together, we're going to get 0. So this is going to be the expectation value for this I here. We do the same for X, we do the same for Y and for Z, and we get the result. That's the result that we need to compute our final probability distribution. So I created a function called expval. You can look at that. It's too long, so I couldn't include it in this slide. So you can look at that in the tutorial session. What it does is it takes the state of interest that we want to find its probability, and the observable that we intend to measure the Cotes qubit with, and then it returns some expectation value. That's what we have here. So now to do that for all the observables, that is I, X, Y, and Z, I iterated over this, and this is the value that I got. So for X, for the identity, this is the expectation value. For X, this is it, and for Y, for Z. So that's it. Now we are coming to subcircuit I for subcircuit V. So if we recall the example that we did before, we would like to compute the probability for this. This is the state that we wanted to find its probability value for. So subcircuit V is going to be 100. So that is from the cut qubit, which is qubit number 2, all through to this qubit, all through to this point. That's what we're looking for subcircuit V. So after we have to initialize the cut qubit to the state of interest, run the circuit to compute the probability distribution for all the states. So out of the 8 states that, because these are for subcircuit V, there are 3 qubits here. And if we initialize the cut qubit to any state that we want to initialize it, which is the 0 state, the 1 state, the plus, and then the plus I state, any one we choose to initialize at the time, we take the measurement and we find the probability distribution. We are guaranteed to get like the probability distribution for 8 different states. But we are not interested in all the states. We are just interested in the state 100. That is the state that we are interested in. So this is the probability that would be used to compute the probability, the final probability for the states, for this whole state here. So remember that this subcircuit V, we have chosen to initialize it with 0 state, 1 state, plus, and plus I state. If we measure this and get the probability distribution, it's going to be for 8 different states. We just choose the state that corresponds to 100, and that's what we did here. So that I did by using this function, which is props cut. So this takes in some initialization and the states that you want to compute its probability for, and then returns to you some probability distribution. So it returns to you some probability values for the different initialization. So for this state here, this is the state that we're interested in. If we initialize it to state 0, then this is the probability outcome for the state 100. And if we initialize it to state 1, this is the probability outcome, and so on and so forth. So the next thing is to combine this result. Combining this result is the same way we did for subcircuits, for the 1 qubit cut. So this is the way we combine it. We've gotten the expectation value for subcircuit, the expectation value for I, for X, for Y, and for Z. And we've gotten the probability distribution for the 0 state, for 1, for I, for plus, and for plus I state. So if we combine them together using the equation I've shown earlier for combining this, we're going to get this. And this is exactly the same as we would have for, so this is just a summary of, if you do this for all the other states, you're going to have it to be equal to the original uncut circuit. So as you can see here, the probability distribution for cut QC is exactly the same as the probability distribution for the original uncut circuit. So that's the point with this multi-qubit system. So I don't know if there's any question, because that's it from my end with respect to circuit cutting or cut QC. There is also the penny lane version. I wouldn't want to stretch this tutorial because it's already too long. And there's also the penny lane version, which I prepared, but because of time, I wouldn't want to bore you too much, except you are interested in it, so you can let me know. If there's any question, we can go over it before we call it a day, or you want me to continue, I will continue.
There's a question in the chat. Gideon, could you read it out loud?
Okay, what was the question?
It's in the Google Meet chat. Yeah, could you read it out loud just for the benefit of those watching video?
Okay, it says, how to be sure that the subcircuits are in fact generating the same expected value of the observable of interest that the whole circuit should be generating, assuming the entire circuit is so large that there is no way to run it. Yeah. Well, That's an interesting question. Thank you for asking that. The point is that I think we'll first of all check this with smaller circuit, apply it to different circuits, and see if this actually works. That's where I will begin. And for sure, I've tried it with several circuits and it works. This is one method to calculate the probability distribution. You can also, there's another method for calculating expectation value, or you can get the expectation value from the probability distributions that you obtain for the circuit after that. So, but I am pretty sure that if you follow the rules, you are going to get the expectation value for the observable of interest for the subcircuit, for the upstream subcircuit that you're interested in. I don't know if that answers the question, or you can unmute and maybe um, tell me if that's not exactly what you're asking. Okay, yeah, so I have done several tests on this, and this is actually my area of research, and I know it works. You can also experiment and let me know if there was any mistake. Yeah, any questions? Should we end it here, or you want me to go over the penny lane version of code QC?
I think this would be a good stopping point because the penny lane part is better if someone can look at the tutorial. So we will leave that part for the tutorial since it's a bit easier to
Okay,
understand and code if you run it yourself versus watching on slides.
yeah. It's you can run it yourself, and then yeah, I know if I had done the demonstration, I would have taken a lot more time. So I wanted to explain the slides, so explain the concept behind it, so that when you go through the tutorials, you can implement it yourself. So everything in tutorial should be fine and helpful if you want to experiment with this. Yeah, thank you all. It was a great pleasure.
Thank you, Gideon. Let's have a round of applause for Gideon for presenting this very recent paper. It's hard to read recent papers, and yet Gideon did a very good job with a really in-depth tutorial.
Thank you. Thank you.
Alberto, did you stop the recording?
Let me a moment.